Welcome to the Internet of Things equation, a podcast when I talk about the Internet of Things domain both from the technical and business perspectives. I'm Łukasz Malinowski, the Internet of Things advisor and trainer. Today I'll be speaking with the founder and CEO of Nextspace. Mark has over 30 years of experience as executive. We will talk about the digital twins and share insights on benefits and challenges of implementing that concept in real life examples. Hello, Mark. Thank you so much for accepting my invitation.
Oh, thank you for the invite. It's a pleasure to be here. I'm glad we got the time zone sorted out. I'm coming to you
Yeah,
from
that
New Zealand today.
like literally you're on the other part of the globe. Please briefly introduce yourself to the audience. So, what you are doing and what's your history?
Sure. As you said, yeah, I've been involved in what might be described as digital twins for well over 30 years now, just to age myself. We originally founded companies in the field of engineering design. I'm a mechanical engineer by background. We've been doing translating data for engineering in the aerospace and defense arena for many years with a company I founded called Right Hemisphere. We worked with Boeing and Lockheed Martin and Northrop and SpaceX and so forth, and had the pleasure of meeting with Alon, who was a customer at the time at SpaceX. We did such things as we developed the Adobe 3D PDF technology, all of the file formats and renderers and structures around that. And we've had some very fascinating projects working with Harvard and University and Nature magazine for publishing the first 3D publications on astrophysics. And so, yeah, quite a long history in engineering and data. And our business, Right Hemisphere, was acquired by SAP back in 2014, but not before a spin-off company, Nextspace, was spun off to take that type of aerospace technology into the construction and built environment. And that's where Nextspace started. So after the acquisition by SAP, after a few years and a short stint fishing and enjoying things, I had to circle back and try and get things right. So there was still a lot to do in my mind with data management around the concept of integrating engineering data and graphics, and GIS together. So circled back and essentially restarted the process in Nextspace, and still, great friends with SAP. But here we are on the journey with Right Hemisphere version 2 in some respects.
That's quite a story. Main theme of our meeting is digital twin, a term that is often overused and misunderstood. Could you explain it in plain English to everyone listening?
No, I can't. I I say that because yes, I do believe it's overused, and I think its importance is also somewhat overrated. I think there are many definitions for a digital twin, and if anyone cares, there's a periodic table on our website which talks about all of the possible aspects of digital twin. From I think probably the two main threads of conversation are about a system which is a black box replication of real world behavior of a system with, digital inputs replacing analog inputs and outputs. And we see, we mimic the behavior of the real world. And I think that's a very valid definition of a digital twin. But other people will refer to, and they think of digital twin, they think of the 3D game engine type fly through of the world and perhaps stopping to, pick up some information about that world by clicking on things. And again, I think they're all valid representations or definitions of digital twins, and I don't think it's valuable to dwell too much on which is the right definition or the wrong definition. I think Michael Greaves, the father of digital twins, has got some good definitions. I think in general it's common to them, and something I would share is that they really need to be a data first approach. Just having a 3D fly through, walk through, yeah, it might be a digital twin, but it's a fairly weak one, I would suspect, in terms of value. The concept of a digital equivalent in a data format is probably the most valuable aspect of the term. Otherwise, yeah, I think it just gets people's tangles up and creates false expectations and differences in what people have in their head when they're having conversations, which is never useful.
I totally agree with you that this is just an abstract concept, like a data structure with additional logic, so it can simulate and behave like the real life device or part that it represents. So you mentioned that digital twins got value when applied to the business. What are the benefits of using digital twins in an enterprise? Because you are doing that on daily basis. So what
Mm.
do you see how enterprises are leveraging that concept?
It's an awful lot cheaper, experimenting with bits rather than atoms. And what that essentially means is if you can create a digital twin where you're confident in the digital representation of it, whether you are trying to make aesthetic choices or optimizations of the way a supply chain works, or where to lay out equipment, or you're trying to understand, a dashboard of a building or a ship or a piece of equipment, having a visual and behavioral equivalent is very valuable, especially if you want to play what if games. Like, what if I change this input? What if I move this over here? These are all things that you can do very easily in a digital environment with very little expense. But actually going out and physically moving things or changing things or creating different scenarios can be extremely risky and costly in the real world. So the digital, twin is a very obvious place to explore and experiment and work on optimization, of a business or a set of assets for, health and safety, performance, or, just aesthetic reasons.
Yeah, I agree with you because basically that's just the abstract concept somewhere in the memory of the computer. So we can easily modify it, we can replicate it number of times at zero cost essentially and run huge scale simulation without investing almost no money and looking at the potential outputs that we might get by modifications. So I think that's a great way to put it. Before diving into details, could you briefly summarize the challenges of actually implementing digital twins? Because theory is one thing, but real life is sometimes totally different. So, what are the main challenges in that space?
It's a big and it's a good question. Certainly, we like to joke that having been in this general area for so long, we've made more mistakes than anyone else in the world of digital twins, and hopefully we've learned from that. But certainly, I think some of the big mistakes that we've seen, or challenges, have been where people assume that a digital twin is a visual thing, and they start a digital twin project by deciding on a choice of games engine or visualization engines at the front, and then working, we'll need some data on that, and then how do we join the data and start jamming data on it. So there's very little architectural thought to the data model around the digital twin. And I think that is the single biggest challenge. If you're going to build a really functional, useful digital twin, one that supports the ideas we were just talking about, which is a place to experiment with, or at least understand in first steps, what the real world is in a very navigable way, then we need to bring together a lot of data together from different systems. And that data might include GIS data, BIM data, scan data. And when I talk about GIS and BIM, I don't mean just the graphics. In fact, more importantly, I mean the fundamental attribution of that data. We have to bring together a combination of graphics and information. We've got dynamic data, from ERP and EAM systems. How many of these do I have in stock might be part of your digital twin query. And there's no point in trying to encapsulate, all of this external source data in the form of a file format, because it changes on a daily basis in foreign systems. Might use SAP or Maximo or products like this, to set up work orders. And all of this data, we've got IoT devices, of course, and these are all, real-time sources of information. And trying to encapsulate them in a file format, I think, is what is folly and not a useful approach. And I think a lot of people do take this approach where we'll just merge everything into a giant, graphics file format. I think that is one of the challenges: is how do we merge? What's a strategy for data merging, not just on a one-time basis for a presentation, but in fact, how do we dynamically merge data into a digital twin that is up to date, potentially sub-second up to date, so that we have a very live representation of the real world twin in an environment. And then we get into the world of data standards. We have representations of data and things within our data sets that are all built to different attribution standards. And how do we join and map not just the different attributes, but the metadata? And when I say metadata, I mean the data about the data. What are the units? What are the maximum minimums? That's perhaps the stricter sense of metadata. So merging all of the actual data, its values, its structures into one common accessible structure is probably one of the biggest challenges, and it's the one that we've really taken head on as a business, is that data unification. Because when you get that right, you actually then have a fundamental backbone for visualization or support of AI training, analytics, simulation, that all can work from a common, data framework. But until you have that common data framework, you just have a whole lot of raw data in a big pile.
Tons of details, and we will dive deep into all
Yes,
of them.
sorry,
But let me underline one extremely important thing you started with, what I called the shiny object syndrome. That people focus on those graphics, of those visuals, those fancy stuff that is not really that relevant, as you said, right? Digital twin is way more than fancy 3D graphics that you've got on your screen, because that's just a representation, and actually, as such, that representation does not give you that much value, because you do not create automation, you do not use IoT devices to look at some fancy 3D graphics all day long. You want to have all data in one place to leverage the data, and the 3D graphics is just something that you can benefit from, but mostly for the visual perspective. It's not value on its own. So I think that was a great point, and I wanted to underline that for everyone.
thank you. Yes, I think it is often a misunderstood aspect of it. The graphics are there because as humans, we're highly visual creatures, and the visuals are there as an interface so that we can understand the digital twin in a way that the computer understands it. So the computer has a bit and byte understanding of the digital twin. How does the computer tell the human about this digital twin? And we use visuals for it. So it's just a visual proxy for a much deeper concept. So thank you for underlining that.
You put that great. So this is way deeper concept than the interface, which happens to be 3D graphic that everyone likes to share on conferences. You mentioned data and quality of data.
Mm.
So some time ago, the data lakes were a very hot topic, but then they morphed into data swamps. So how can you ensure that the digital twin, which is some form of data structure, really represents the quality of data and it's not drifting into that data swamp category?
Yeah, it's again another a big issue, but certainly I think uh, a lot of this comes from the hope and the dream around AI, and people think, well, AI to use it, we need to get all of our data together in one place, and so people say, well, let's just put it all. But the problem is, you just put a whole lot of raw data on a big steaming heap in the middle of which is a data lake, and then hope AI will just sort it out. Is not really realistic. I haven't seen that successful. I mean, it may be, but it's certainly not within the engineering environments. And I think a good digital twin data backbone is absolutely critical and foundational if you're going to have an AI strategy. So AI is about training systems and about to say, look, this is the data, i.e., this is our digital twin state. At this time where this happened, and this was a good thing that happened, or this was a bad thing that happened, and you carry on and you train an AI system based on what was the state of the world at this point, and then something happened, was it good or bad? And then we look in the future and say, well, this is the current state, what do we predict is going to happen? So I mean, that's the very, very simply, that's the sort of foundation of AI concepts. And I believe very strongly that AI concepts are expert support systems, not expert replacement systems. Just to be very clear, that may change, but certainly in the field of engineering and where there's money and, and legal responsibilities, challenge around data lakes is that I don't think they need to be, explicitly a data lake. I think the concept of a virtual data lake is just as powerful, and in fact, arguably, better, because your sources of truth, as we talked before, for a digital twin, are going to be potentially across multiple, daily use systems like SAP Maximo, CAD, BIM systems, IoT sensors, and so forth. So there's a whole field of rapidly changing data that needs to be amalgamated in real time, and I'm not sure that data lakes necessarily play a great role in that. They may, but data lakes really, to us, are just another source of data that still needs, mapping to common data schemas and agreed standards for the digital twin. So yeah, I don't think data lakes offer as much as they promised, and certainly they're a source of data. I think more fundamental to the data problem is what we describe as data ontology, which is the idea that you have a whole bunch of things in your organization, or assets, if you want to call them that, and those assets will be things of interest to engineering, manufacturing, finance, maintenance, and so forth. Typically you're all dealing with the same physical things, but everyone likes to organize them differently. Like finance will have a different set of structures for the same things. We learnt this even just at Boeing, a manufacturing engineering group, and build, engineering hierarchies. And as soon as manufacturing get the same data, they reorganize it into which things are coming together in a work cell. And so they restructure it, and they take the engineering attributes and they throw 80% of them out, and they add another 20% of attributes to the same things for their purposes. And as soon as that data moves over into maintenance processes, the same thing happens. It's reorganized and regrouped to suit the needs of the maintenance. The finance people want reports, and so everyone's talking about the same things, but with slightly different sets of attributes and slightly different organizations and structures. And this is where standards come in. So, people talk about this standard, the IFC, which is a very loose standard. It doesn't really describe in detail the attributes of things. But this is the biggest, single problem, I think, and a data lake doesn't solve that. So structuring the data and being able to map from one data schema. So if I have a representation of a pump, I might call it, P for pressure, or I might call it pressure for pressure, I might call it the full name pressure. I might have it in bar in one, I might have it in PSI in another data set. But if we know it's the same pump, we still got to join all that data together. So we need some way that actually, systematically in real time maps all of the different attributes and what they really mean to one common agreed standard. And people often ask us, what standard do we adhere to? And we're not. I don't think that's the job of a digital twin. The digital twin is there to be and to encapsulate whatever standard you desire, and provide a set of tools to map from all the standards you already have to the one that you want to use currently for your purposes of a digital twin analytics, and then also be able to write to a standard that you may want in future. So I think you have to take standards out of the equation. I think that's a very important part of a digital twin solution, is that. And I don't see data lakes solving that problem. They just move the data problem from 20 different places into one place, but I don't know that they necessarily solve a lot of digital twin problems. Anyway, I'm sorry, that was probably a slightly longer answer than you were looking for.
No, that was actually great, because once again, you mentioned a number of important topics that I'd like to underline for everyone. So first of all, the digital twin can be thought as the data proxy, as you said, right? So because it is basically a structure of data that points to different source systems. And you mentioned the source of truth, which is something that is actually way more difficult than it might be perceived on, right? Because just to identify the single system that always got the correct data, when you've got the distributed system of number data sources, databases, that's not that easy task, actually. So this is something I would like to ask to go back to. But then you mentioned the standards and that expectations, and the questions regarding standards, and that reminded me the hype around NoSQL databases. So everyone was happy because you can dump whatever garbage you've got into NoSQL database and then pretend that the job is done. So the same as with data lakes, right? So to keep all the garbage in one place, like database, NoSQL database or data lake, doesn't really do much. Like, because you need somehow to understand the data in order to act on it. Because if you cannot act on your data, then that data is basically worthless and you're just wasting your storage. So that was such a great point, and I totally agree with you. We should start with standards and with defining the both the source data, the raw data, and the target form of the data, and then we can talk about digital twins, because digital twin by itself doesn't help you if you've got data that is totally desynchronized all over the place. So that is such a great point. You've got tons of experience in the data ecosystem. How can you help customers, companies to make their data actionable?
Well, I think it comes back, to that thing of getting on top and getting control of your, data standards with an organization. I think these are unavoidable, whether they're, ISO standards or just proprietary data structures from different systems. We encourage people first, to realize they're going on a journey with the digital twin, and making their data actionable, is very much, I mean, that's the goal, the ultimate goal of the digital twin. But the first step is really, to everyone to take a deep breath, and from the board, down to the guys in the shop, everyone to stop and say, look, what are the things that are important to us? What are the goals that are important? We want to optimize efficiency, of our supply chain. We want to optimize our material workflows within a factory. We want to optimize our maintenance processes. So, with predictive maintenance, we want to make sure that we don't have health and safety issues. You want to predict this. And so understand what you want to do, and then how it relates to the things in an organization. So the first step is really to use an old, Greek concept, as I mentioned before, of ontology, and that's about sitting down and saying, these are the things we care about. These are the attributes of these things that are likely to be important when we consider them. And then the next step is, well, what are the relationships between one thing and another that are also important? This machine supplies, this volume of output to these next machines, or this type of thing, or this pipe is connected upstream from this pipe or downstream from this. And so there are potentially many different dimensions of relationship to consider that operate between things, not just CAD hierarchies, which are parent-child, but functional or support relationships that you might want to be analyzing. So building up a digital twin infrastructure that outlines all the things of interest, their categorization to help structure them and compare them, the relationships with one another, and then building up a data structure which can then say, well, what are all the useful visual representations of these things, so that we can understand and communicate to people. So I think that's one of the first things, to make data actionable, is to actually bring it together in a common form where it's all understandable by anyone who's in the room, from finance to engineering. We all agree this is a propeller, this is a pump, and these are the attributes that are important to me, and here's the complete set. And so bringing it together is the first step in the digital twin. And then once we do that, then making that data available through a visual interface, so humans can understand the state of things at any given moment. Because if we run analytics and prediction and so forth, what do we do with that data? Well, ideally, we would put that data back in the digital twin in the form of a new state in the future, and be able to visualize it and see it and compare it with the last one. Put in an API around common access to an absolutely common agreed data collection that is a real-time data collection of static and dynamic information that we can access, run analytics, run visualization. That's the first step in being able to utilize real world data that's been turned into a digital form. And it's all about accessibility, whether it's visual accessibility or whether it's external accessibility for other systems and software. So the API first approach to connecting to a joined ontology understanding of the data. I think those are the two really critical aspects. And once you have that, then you really have a whole lot of options. I mean, we see the world of AI simulation has just been so exciting, but ultimately they're going to be built by experts, in particular analytics, university companies. There is no one company that, potentially is going to have all of the answers or simulation analytics. However, if you have a raw data backbone set up and a way for any system to get in, use data, analyze it, produce results, and then a place to put it back that can be shared with all the other data, you have the perfect, storm for building AI and learning, machine learning, AI analytics around the complete set of data that's there in a structured format. So we see that as the most important is getting your data ontology right. In summary, for the digital twin, and that's what makes it usable and actionable.
What you said about different perspectives on the same digital twin, like every stakeholder, every department got a bit different perspective of the same asset. So that basically allows us to create that multidimensional metrics, so to speak, that we've got the same data, but maybe the relationships and maybe the attributes are different depending on the stakeholder. And having that digital twin as the source of truth, that really allows us to create those multi-dimension, multi-viewers type of scenarios, which are crucial. And what you said about the machine learning and artificial intelligence is very accurate. So the models are as good as the data that you use to train them. So if going back to our conversation about data lakes and data swarms, if you've got poor quality of data, you cannot expect to have great results both from AI and from digital twins as well, because they will just represent the quality of your data. And if you've got your data tightly organized, then you can really leverage those approaches. But let me ask you a tricky question, because the initial implementation of digital twin is very demanding. But from my perspective, what is even more difficult is keeping that digital twin up to date and introducing changes to the structure, to the functionality, while having this whole setup operational. So, how can you enable that iterative approach to improve your digital twin, to add some extra capabilities, some maybe extra attributes, uh, and somehow manage the complexity that you are working with?
So the two sort of parts to that question, I'll address the first one is keeping things up to date. Whether that external data is a new BIM file or it's the next second of IoT data, whatever it is, understanding that a data feed has changed and how that impacts the greater model. And perhaps to answer that, the first thing we would say is, people often say, the digital twin is the source of truth, and we would sort of say it is in a way. It's not. The digital twin doesn't have to be the source of truth. It can be, like we store data, but ultimately where that, the sources of truth may be many and varied, and the job of a good digital twin is to bring all of that data together real time to a single access point for truth, whereas the actual truth may be in many different places, including stored, in the cloud storage of a particular digital twin, but it's also likely to exist on an IoT sensor as the source of truth for that, or in an SAP data structure or Maximo data, whatever it is. And so the first job is to be able to bring that data together in real time. Now, in terms of merging it together and understanding changes and deltas, the most fundamental aspect, we see of the digital twin infrastructure and ontology is what we call GUID management, or global unique ID management. So in simple terms, it's about understanding what things are the same as, the thing I've already got, or different, or what's changed. So at the very heart of it, a GUID management system, or just unique ID management system, is really critical. And it means that when we get a change from a BIM file or a sensor, the first step is that we can identify then whether this is the same thing as we already know about. Do we have this thing in here? And if so, do we have all of the same attributes that we had last time? Yes or no? Do we have all the same values for those attributes as we had last time? So it's a systematic approach to comparing, is it the same type of thing? Is it the same exact thing? Has it got the same attributes? Has it got the same value? Has it got the same metadata? But to enable that check of data requires that you understand absolutely the rules about whether something is the same thing or a new thing. When I put in a new wall in a building, is it the same wall with different attributes, or is it a new wall with is it a new thing? And both are arguably valid approaches. So there's a lot of complication potentially in the rules of what people consider new data versus updates to existing data, and it's the way that you handle that and the system that's there. So we've spent quite a lot of time on tools to manage unique IDs, using what are called foreign keys. So we identify unique identifiers that have come from external systems. We map them all together and we put a global ID over the top. And so that's the foundation of managing change is first to get on top of being able to identify what things are the same, what data is the same, what's different, and so forth. Once you've built, your first, ontology, you've all sat down and said, look, these are the things that we care about. These are the attributes. These are the metadata. You then want to be able to describe, put that into the system. So we make it pretty easy to write that, and we will, inherit data from spreadsheets or BIM files or GIS, whatever it is, and create a starting structure. But the moment that we join, potentially like a piece of IoT data to a piece of BIM data, which exists, on a network, we've got potentially 2 or 3 sources right there of information that probably doesn't overlap a lot, other than maybe the lat long is recorded in both the GIS and the BIM system. But we have a set of attributes which might be, the owner of the wall. Well, let's talk about a pump that comes in from a building. We're going to have, an asset ID. We're going to have pressure and so forth. Then we want to link, and we want to cross-link the data from the sensor, which gives me the current pressure and temperature. I'm going to take the GIS data, which says this is where the pump is in the world. And so I can bring all that together and I get, amalgamated set of attributes which have come from BIM, from GIS, and from the IoT. And then someone might say, well, what our big challenge is we want to be carbon neutral. So we want to start measuring, the carbon footprint and energy usage. And so the ability to go in to the type of thing called a pump, of this type of pump, and add a new attribute, which is, energy, consumption and calculated carbon footprint as new attributes. And so again, the ontology system we have is designed so that anyone within, a few seconds can add any attribute they like to any type of thing, assuming they have administrative capability. But this is all about taking control of the attributes and the metadata of your digital twin external to the BIM system, external to the IO. Data coming in is really just, they're contributors to the data schemas and the data structures that you want. What's more important is be able to take control of those data structures. So you want to be able to add, modify, unify, join. And again, that's probably much more at the heart of what a digital twin system is all the tools to handle that GUID management and the data joining, the visualization being very secondary to that, and something that just naturally falls out if you get the data part right.
You mentioned something extremely important that we skipped up to this point, which is the metadata. And I truly believe that the data without metadata is basically worthless, because you need to understand those bits and pieces, and metadata is the language that describes them for you. So you greatly set the context to that digital twin. It's not only about data, but it's also about the metadata that stores information about the data itself. And let's go a bit further, because I'm the IoT person, and the Internet of Things is a bridge between the physical and digital worlds. And you mentioned IoT yourself a few times. Could you explain how the Nextspace is leveraging the IoT to get data from real life, like real time data, and feed it into digital twin structures and leverage that data?
Sure, I'll get outside of my pay grade for some of the technical aspects of that. In short, we're using the same GUID analysis. To us, an IoT data source is the same as any other data source. It's a thing, a virtual thing, it has data which changes temporally, and we support the concept of attributes which change over time. So we can animate that world. And we map device. So we may have a sensor which is measuring temperature, humidity, carbon dioxide in the air, for example, a room sensor. So we have one sensor, we have a sensor thing. It has three attributes which are dynamically changing, and we provide the tools that will connect that up from various IoT hubs, like Azure, Google, AWS, and so forth. We use Graph, QL, and so forth. There are many data connection tools that we have to get them, but ultimately we treat an IoT source as a piece of data linked to a sensor thing, which we then map to an actual thing. So in a digital twin world, we will have potentially a representation in a GUID format, in a graphic format, in a database format of a pump or something, or a room, or the actual sensor unit itself. So we'll have a room, and there will be an object in that room which will be registered in the database, which is the sensor, and it will have a visual proxy. It might be a box, or it might look like a beautiful thing with little dials and all the numbers on it. Doesn't matter. It might be a 2D representation from a schematic diagram, but all linked together. And what we do is we map the values out of the IoT to that database representation through the unique ID management. And so we go, that is that thing, that is that thing. And so when we type in the identifier of the sensor unit, then we immediately know that the mapping, that's our foreign key. We know that all of the values will then map automatically and in real time to the attributes of the physical sensor unit that we represent in the real world, either in 2D or 3D or what have you. And I'm sorry that's a slightly complex, but fundamentally it's just about identifying what is a thing and what's a set of a data source that is contributing to the complete attribution of the room or the sensor unit or the pump or what have you.
Nextspace provides that fancy 3D representation of digital twins, and as we said, this is just the output, one of views that you can have on the digital twin structure itself. But maybe you could give us the end-to-end walkthrough of your solution. So how you take data from those sources, manage it, and present in that fancy 3D graphic.
Sure. Perhaps a diagram might be useful at this stage. So this is a very, high level representation, but essentially we do a data audit with companies, and I think it's first, important. Our system is designed for, typically partners or customers to do that work. We do find ourselves helping people get started, and we provide the training, but we're not a services company. In fact, one of the things we've noted is a lot of digital twin product offerings, to be blunt, seem to be more like thinly disguised services contracts rather, than an actual product to join things together. So what we provide is a platform, and so this is what a customer will do or a consultant will do for a customer using our platform. And they'll bring together data from IoT, and so forth, different systems, and they might prototype it using largely static to start with, and then as the data schemas and everything are managed, they'll start joining the dynamic data. But the first step is working through the API, and this is done through drag and drop processes. It's all no coding typically to bring data in. Special cases, there might be some coding, but most of the time this is just drag and drop. But everything comes into this ontology state engine, and we have some AI tools to help join data together automatically, to connect standards and metadata and so forth. And then we have API, and we say, well, I'd like to visualize that, and we can choose your visualization engine, Cesium, Unreal, Omniverse, and can be Unity as well. There's a bit of discussion going on about adding a Unity connector. But ultimately, all is that we feed to a visualization module is a graphics proxy, like a 3D graphic with one attribute, which is the unique ID. All of the other data about that thing is actually handled in a cloud-based database. So regardless whether you're working in Cesium, Unreal, Omniverse, or a simulation, or any external system, you're all looking at a common database of information about the same thing. And so if I make a change, I can see data change simultaneously in all these destinations, and vice versa, right back. So that is really the overall workflow. If we go into a bit more detail as we bring data in, we're looking to, say, is we deconstruct all the data. So we store the original files, but once we have the data and we unify it, we generalize, GIS, BIM, graphics, spreadsheets, whatever it is, into this general ontology idea of these are the things, and then, what can we uniquely identify things? Can we classify them? What attributes, media, document, relationships, what can we learn from the data that's coming in, and then we compare it to what we already have, as we discussed, and say, well, do we already have one of these types of things? Do we have this specific thing? Do I, have to extend my data schema or modify it? Do I have to change my metadata? And then, what visual proxies have been brought in? So we see here an example of a valve, and this is part of, an entire plant of data. So this is all done automatically. It gives it a global ID, and then it says I have found, through all my different data sources, I've found a 3D CAD models of this format and that format. I've found point clouds. I've found what are called, process instrumentation diagram symbol that can represent that valve. I've found isometric symbols. I've found all of these different attributes from many different systems. I've found all these linked documents. I've found these IoT references. And so all of this, is done either automatically or semi-automatically to generate, a connection of, all the data to just a pure abstraction of this thing, which is nothing more than an ID. And so if, the data about how many in stock change over here and, SAP world, I will see that instantly because I've recorded the entire trail of GUID information down to this. So when I touch on it, I see that data change. And likewise, once we have those things, then we have to build, a structure of what thing is related to what other thing. And that all sounds very abstract, but it really works. And what it does is it creates, views like that where you can go through and just touch on things in any environment and pick up all of their data and navigate to their diagrams. I can freely go from, point cloud scans and CAD and find my way to the, exact PNID, and I can navigate to another object and fly to it because everything's connected. And I can leverage my existing document management systems and IoT data. There are no rules as to what the source of truth is. You have as many as you like. And so it's about constructing these. But it's a process that, we believe is the fastest and most future-proof way to build a digital twin. A scene like, just seen on the screen is, typically done within a day's work to get, that or less. The large models, we have interfaces into all sorts of different plant and process and CAD systems and data and so forth. But, there's detail. So it does depend, but it's very fast to build up at least the digital replica. And then once you have that, you have the framework to start connecting in your predictive analytics or adding more sources or extending the attribute structures or, data mapping. And there's always, work to do, but to get started is pretty fast. And you typically will use a BIM model or a GIS data set or a spreadsheet even. In some cases, we have no GIS data. We just bring in a set of things and relationships which are represented in a non-spatial space. That can be a start, and then you can add the spatial data later or the visual representations later. So there's no penalty in getting the data structure wrong to start off with.
Let me say that this is very solid solution design. I've done some database designs like back in the days, some integrations, and what you just show and walk through us, this is really well thought through system and the data flow that you're using. And I love the setup that you've got those number of destinations, those like 3D visualizations and analytics, but all of them work from the single data structure. So if you change something during the simulation, you can immediately see that on the visualization side. I think that is really core in terms of creating solid systems, and always look at the most recent data, right? Because those 3D visualizations are just like a view on your actual data, which is really, really good. Thank you so much, Mark, for taking us through this setup and for sharing your knowledge on digital twins and some real life challenges that you faced, and as everyone who tries to implement that concept in the actual environment. So what is the best way for viewers to contact you to learn more about digital twin and maybe ask you about the solutions that you offer?
We'd encourage people to go to our website, www.nextspace.com. I guess I'm old fashioned in the way I say that, isn't it? Just say nextspace.com now. And to go to the website, and there's also a tool that you can try just the visual side of it yourself for free. So you can download, sign up for an account, and just start trying with drag and drop in a basic version. But I would say go to the videos. There's a lot of information on our website. If you go up to the little hamburger on the right and go to videos, you can see very detailed videos which talk about the full data workflows. Sure, there's a lot of graphics because people love them, but we'd encourage you to dig a bit deeper into the site. There's a lot of information there on the return on investment, that people have found from, and how they've achieved it with digital twins. Technical details on what is part of what we offer and what other people offer in digital twins. So yeah, great resource there. If you're building up the business case internally to start a digital twin journey, and it is a journey. Yeah, there's a lot of good background there, and there is contact. If you contact, I think sales or help at nextspace.com, but it's on the website. I hope that was useful, Lucas. And again, thank you for the invitation to speak. We love talking about this as well. So, thank
Yeah.
you.
Thank you so much. You really provided tons of value and tons of experience, and that's all that is important, in my opinion, to share that experience with everyone willing to start their IoT journey or digital twin journey, as in this specific case. Once again, thank you so much for taking time to meet with me today.
A real pleasure. Thank you.
Thank you for listening. Go to thefingers.com to find more materials about the Internet of Things domain. My name is Łukasz Malinowski, the Internet of Things advisor and trainer.